So let's look at this test review. Question number 1. It says use a trig identity as the hint that you were given. That means on the test there could be some trig version or some limit problem. For this one, there are actually two ways to do it. First thing I looked at doing when I made out the key was I said let's try factoring and make this 1 minus cosine of x times 1 plus cosine of x. And then said, okay, well that would become the limit as x goes to 0 of 1 minus cosine of x over x, and then also the limit as x goes to 0 of 1 plus cosine of x over x. Well, the problem I run into here is this one is 0, because that's one of our trig identities, or one of our trig limits that we had to learn. This one would be 1 plus 1, so 2 over 0. That's undefined. Well, 0 times 0 is an indeterminate form. Well, no, sorry. 0 times an undefined is, and this is still indeterminate. So that's 0 over 0 basically. So we can't make a conclusion. So instead of doing that, let's try a different route. And what I would do is realize this right here, 1 minus cosine squared, is a trig identity that's going to make this problem much easier. Hopefully you remember that sine squared x plus cosine squared x equals 1. You need to commit that to memory from pre-cal, and we'll actually use that. So if we were to move this cosine squared x to the other side, 1 minus cosine squared x is sine squared x. So this right now is the limit as x goes to 0 of sine squared x over x squared, which could be rewritten as the limit as x goes to 0 of sine of x over x times the exact same limit as x goes to 0 of sine of x over x. That would be sine squared and x squared. So we know this limit. Well, that's 1. And we know that limit's 1. 1 times 1, we get our answer of 1. For number 2, find the limit as x approaches 1. Well, this one you don't have to test both. You only have to test both on greater than or less than. This one, what you really have going on here is we have a parabola that moved up 4, and at 1 it jumps off that parabola and goes to the y value of 2. Well, the limit would be right where that y value is. We don't care about this point down here. That does not affect the limit. That's just the y value. The limit as x approaches 1 of our function is 1 plus 4, which is 5. It's right where that y value is. At 1, we're up at 5. So, question number 3. Oh, by the way, these tell you whether these kind of questions would be calculator or non-calculator. So this is a non-calculator question. Limit as x goes to pi of tangent of 5x. So you need to know what a tangent of 5 pi is, because direct substitution, tangent of 5 pi. Hopefully you remember that a tangent graph goes through 0, has a vertical asymptote at pi over 2. Goes through 1 pi, has a vertical asymptote at 3 pi over 2. Goes through 2 pi at 0. So 1 pi, 2 pi, and all the odd pi over 2s are our vertical asymptotes. So 5 pi is actually just 0. Every 1 pi, 2 pi, 3 pi, 4 pi, 5 pi are all at zeros. Okay, number 4. I have to confess now. Ignore these answer choices. I changed this problem, and I forgot to erase the answer choices. So, limits to infinity are horizontal asymptotes. This one, the degree on top is the same as the degree on bottom, so it is a Betsy. So all we have to do is look at the leading coefficients. We're looking at the coefficients. 5 over negative 2, or negative 5 halves. That is our limit. And we're done with that one. And that did not match those answer choices. So, number 5, at what values is this function discontinuous? Well, the only time this denominator equals 0 is when x equals 2. So it's discontinuous at x equals 2. So let's write that. Discontinuous at x equals 2. And it was a non-removable, says what type? So I'm going to go ahead and say non-removable just to help you refresh your terms on those. Non-removable, which means it has a vertical asymptote. That's an arrow pointing to. It goes both ways. And non-removable is vertical asymptote. Vertical asymptote is a non-removable discontinuity. So, maybe I should, I don't know if you can tell that that's our arrows. So, just so we have that there. Where is this function discontinuous, or where it's not continuous? Well, this function is not continuous at 3, but we're only looking at it after 5. So this is a hyperbola, a rational function that moved right 3. It has a vertical asymptote, and then it does this. But we actually don't start drawing it until 5. So it's somewhere, whoops, I meant to switch to an eraser. So it was somewhere, ooh, a little bit ginormous of an eraser, sorry. So it's not until 5 that we start drawing that, and it becomes approaching the x-axis. Before that, we're up at 1/2. Now I don't know whether that's at 1/2, or so I know this 1/2, and then it stops. So the question is, do these line up? Well, let's find out. Let's find the limit. Well, I know the limit as x approaches 5 from the left of our function. That's just 1/2. The limit as x approaches 5 from the right of our function is plugging in 5 into here. 1 over 5 minus 3. Oh, it is 1/2. So those two functions actually line up at the same point. So we have this kind of a graph. It is continuous everywhere. Continuous from negative infinity, for all real numbers, from negative infinity to positive infinity. Or you could have used the capital R for all real numbers. Now, here comes everyone's favorite problem. Your favorite problem and mine. Multiplying by a conjugate. We haven't practiced that enough. But we should be, maybe by now, the time that you're watching this, we've practiced this more. So let's multiply by the conjugate on this one. I see two terms. And that the square roots are often the ones you want to get rid of. So we're going to do the conjugate of the square root terms. So I'm going to take this function and multiply it by those same two terms, x plus h minus 9. Don't change anything inside the square roots, on top and bottom. Square root of x plus h minus 9, square root of x minus 9. The only thing that changes signs is the sign between those two terms. So from a minus, the conjugate is a plus. Everything else is identical. Now, make sure you write small when you fill this in, because this doesn't fit in that box very well. It's still a limit as h goes to 0. My denominator has an h, and it has a square root of x plus h minus 9 plus square root of x minus 9. There's our denominator. The numerator, let's FOIL, and you only have to worry about the first two terms. Square root of x plus h minus 9 times the square root of x plus h minus 9 is just x plus h minus 9. You don't have to worry about the middle terms because you're going to get a positive and a negative, because we have a positive term and a negative. So when you FOIL that, the middle two terms, the outside and the inside, go away. So the only thing else we have to worry about is the last two terms. And that's a negative, and there's more than one thing. So put a parentheses or you'll make a mistake. And that is x minus 9. So let's clean that up. It's still a limit because I haven't evaluated yet, haven't plugged in 0, because if we plug in 0, you'd actually get 0 over 0 for this problem. I forgot to tell you that first. I just used the hint to start it with the conjugate. So our denominator is still x times the square root of x plus h minus 9 plus the square root of x minus 9. The numerator, well, if I look, I have x minus x. That's gone. Those add to 0, so those subtract out. Negative 9 minus negative 9 is negative 9 plus 9. Those are gone. The only thing left on top is an h. Well, that's nice, because now I have an h and an h that divide out. Once we removed our discontinuity, we now can evaluate this limit. Let's rewrite it though first. The limit as h goes to 0 of 1 over square root of x plus h minus 9 plus the square root of x minus 9. h goes to 0, so that makes that go to 0. So this is 1 over square root of x minus 9 plus the square root of x minus 9. Hey, I wrote smaller than I did when I worked this out. So we end up with 1 over square root plus the square root is 2 square roots. 1 over 2 square root of x minus 9. It's not a very pretty answer, but that's the answer to this problem. Okay, and I've already made the copies for this one, so I have to confess, there's another typo. I think, let me make sure I'm looking at this. Yes, on this problem, this should have been a 3. I goofed, so my fault. So let's work this one out. Find the values of any discontinuities. Well, and find out if it's removable or non-removable. So let's factor both the numerator and the denominator. So f of x equals, what multiplies to give you negative 28 that adds to give you a negative 3, not 4? Well, x minus 7, x plus 4. Would have 3 worked? No, because that would have been 21. So, yeah, I was thinking, I wanted it to be, okay. Anyway, so the denominator is x squared minus 9 factors to x plus 3 and x minus 3. There are 2 spots where this function is discontinuous. Anytime the denominator is 0. So it's discontinuous at our vertical asymptotes because they don't cancel. Discontinuous at x equals positive and negative 3, and they don't cancel out. They're vertical asymptotes, so they are non-removable. Holes are removable discontinuities. Vertical asymptotes are non-removable discontinuities. So there's the 2 things we needed for this one. Number 9. We want to find the average speed. Hint, average rate of change. Average rate of change is the slope formula, which is f of b minus f of a over b minus a, but we're using h. So h of 4 minus h of 3. You could write it the other way around, but you have to write it the other way around in the denominator also. So I'm just going to write it that way. So h of 4, you plug 4 into negative 16 times 4 squared plus 72 times 4. I used a calculator, and if I didn't mess up, that is 32. Then minus h of 3, plug 16 times 3 squared plus 72 times 3 is negative, or minus, we get a 72. So h of 3 is 72 over 4 minus 3, or 1. So 32 minus 72 is a negative 40 over 1, and units are important. H, did they tell us? H was in feet, time was in seconds. So this is, numerator was feet, denominator was seconds, so it's feet per second. And that would be B. Number 10. We want to make this function continuous. To make a function continuous, well, we have to look at both of these functions continuous. X squared is continuous. A number over a constant over x is continuous as long as x isn't 0, and we're only looking at it bigger than 3. So both of those pieces are continuous. So to make the function continuous, we're going to have to set these 2 functions equal to each other. But they only have to equal each other at one value of x. And the x that we plug in is when we're switching between the 2. We're switching at 3, at x equals 3. So plug in that 3, and you get 3 squared is equal to c over 3. Or 9 is equal to c divided by 3. Multiply both sides by 3, and you get a c value of 27. And that value of c would make these 2 functions continuous. So let's look at the backside. The first one is a rational function that's moved right 1, and it's negative, so it's flipped over. So that's the transformation stuff that you may have done in Algebra 2 and Pre-Cal and college algebra. So I know what this graph looks like from teaching all those courses. So It has a vertical asymptote at 1. It is a non-removable discontinuity. If you don't know, I made this a calculator question, so you should graph this. Negative 2, well, if I plug in 1, I get 0 in the denominator. If I plug in 2, you get negative 2 over 2 minus 1. Negative 2 over 1. If I plug in 2, I'm at negative 1. If you plug in 0, you get negative 2 over negative 1, which is positive 2. So this one is, what happened was it flipped over. Normally it's in the first and third quadrant versions. Well, this is reflected over, so it's in the second and fourth quadrants. So there's what the graph looks like for a rational function. You could have graphed it on the calculator. I'm doing this whole thing without a calculator, just for as much as I can. The only ones I used it for were the average rate of change problems on the previous page. Now, as we approach 1 from the left, this little negative means from the left, so go towards 1 from the left, we are going up forever. The limit does not exist, but that is not a good enough description. We know it's going to infinity. Hey, that looks like the mask of a Teenage Mutant Ninja Turtle, but never mind. Moving on. Number 12. I see a limit to infinity. Limits to infinity are normally Bobo Boccia Betsy kind of problems where we look at horizontal asymptotes. Well, this one, 1 over n, that's bigger on bottom, or a fraction that goes towards infinity. This denominator is going to get bigger and bigger and bigger, which makes that whole fraction go to 0. So we're at 4 plus 0. So that limit is 4. Limits to negative infinity are the same as limits to infinity for 90% of the problems, 95% of the problems. The only time they're not are square root or exponential, and this is neither of those. So we look at the degree. Ignore the 4 is just a 4. That's a constant. We're going to leave there. This is a degree of 1. This is a degree of 1. So it's a Betsy. This was a Bobo over here. Bigger on bottom, so that's why it went to 0. This is a Betsy. So we look at the coefficients, which are 2 over 1. So we end up with 4 plus 2 over 1, or 4 plus 2, which is 6. On number 13, we have a vertical asymptote at 2. And it is a non-removable discontinuity. Hopefully you remember that we've studied that this is a hyperbola in the first and second quadrant because the squared moves it up. So it's up here like this, and it's up here like this. And if you noticed, I made this a calculator question, so even if you didn't know how to do this one, you could graph it and see on the calculator. So the limit as x approaches 2, from both sides it's going up to infinity, so we put infinity for our answer. Number 14. Number 14 says we have a table of values that show 2 continuous functions, f and g, as well as their derivatives, but you won't need the derivatives for this problem because that's not until the next 6 weeks. The function h is given by h of x is equal to f of g of x minus 6. Explain why there must be a value of r between 1 and 3 where h of r equals negative 5. The only kind of problems we've seen when there must there be, or that is the only existence theorems we've talked about so far are the intermediate value theorem. So this is an IVT problem. So first off, is h continuous? Well, I know f and g are continuous, and a composition of 2 continuous functions minus a constant is still continuous. So h is continuous. So we'll put that in our conclusion. But I need to find out what h of 1 is and what h of 3 is. H of 1 is equal to f of g of 1 minus 6, which would be f of g of 1. Go to 1, go to g. Ignore g prime. We're not using the f prime or g prime. Those are derivatives. That's not till later. G of 1 was 2. So that's f of 2 minus 6. Not f times 2. That means the function evaluated at 2. Function evaluated at 2, f of 2 is 9. So 9 minus 6, which is 3. So now let's do h of the other end, 3. H of 3 is f of g of 3 minus 6, which would be f of, well, g of 3 is, go to the row 3, and g is 4. So this is f of 4 minus 6. F of 4 is negative 1. Negative 1 minus 6 is negative 7. So we went from a y value of 3 to a y value of negative 7. I forgot my equal sign there. If we go from 3 to negative 7, we had to pass through negative 5. So here's our conclusion. Since h of x is continuous, or since h is continuous, because we talked about compositions of functions are continuous, is continuous, and since h of 1 equals 3 and h of 3 equals negative 7, because of the IVT. So by the IVT, there must be an R. I guess I could say on the interval. Must be an R on 1 is less than R is less than 3, where h of R is equal to negative 5. And there's number 14. Number 15, find the limit at negative 2. If I try plugging in negative 2, what happens? I bet you get, well, that would be negative 8 plus 8, that's 0. Well, you get 0 over 0, so we can't make a conclusion. So I look at this. What else can I do? I notice that we have a factor of x and a factor of x, well, a factor of x squared and a factor of x squared. Factor out an x squared. That becomes x plus 2. Now, my x plus 2's divide out. I'm left with a simpler version of just x squared. So that it is an equivalent version except for one point where negative 2 is undefined. But now we can plug in negative 2 and see what you get. Negative 2 squared is negative 2 times negative 2. 4 is the value of this limit. And let's just keep on moving. We're down to almost to the bottom. 1 over x minus 2 is a calculator question, but I'm doing this without a calculator. It is a hyperbola or rational function that's shifted 2 to the right. So it is in the first and third quadrant. 2 from the, is that a plus? It's kind of blurry on my screen. 2 from the right is going up forever. So infinity. That's a sad looking infinity symbol. It still looks like a person to me, or an alien or something to me. Never mind. It's getting sidetracked. Okay. 17, I notice if I plug 3 in, I get 9 minus 18 plus 9, and that's going to give me 0 in the denominator. So, it is a non-removable discontinuity. It is a vertical asymptote at 3. Actually, what this graph looks like, if we factor the bottom, we have x minus 3 squared. So, let's see, what was that? I'm going to look at 3. We have a vertical asymptote. And you plug in 0, you get 3 over 9, you get 1/3. You plug in 2, well, that'd be 2 minus 3, that'd be negative 1 squared, which is 1, 3 over 1, so it's up at 3, so it's going like this. If you plug in 4, it's going to be at 3 again. It's a mirror image. Whoops, I didn't draw that very well. I ran out of room. But as you can tell, at 3, because we had a vertical asymptote there, that's my, and it's going up on both sides, infinity is our solution to this, or is the answer, is how we describe where this limit's going. Let's see, number 18. Can I plug in 3? 9 minus 9 plus 2. Well, let's see. Why don't I just go ahead and let's factor it. It won't ever hurt to factor. That would be x minus 2 and x minus 1. The denominator x minus 2 and x minus 3. And to look at what multiply gave me positive 2, the dad gave me negative 3, negative 2 and negative 1. What multiplies to give you 6, the dad's to give you negative 5, negative 2 and negative 3. Cancel out my x minus 2, so yeah, it would have been 0 over 0. Now I can plug in 3. 3 minus 1 over 3 minus 3. Oh, it's still undefined. It is a vertical asymptote at 3. Well, what would that look like? At 3, it's a calculator question. You can graph it on the calculator. I just know there's a vertical asymptote there. If I pick a number smaller than 3, like 2, 2 minus 1 is 1. 2 minus 3 is negative 1. 1 over negative 1, it's down here in this quadrant. If I pick a number like 4, something on the other side of my vertical asymptote, 4 minus 1 is 3, 4 minus 3 is 1, it's up here, it's doing this. So 3 from the left is going to negative infinity because we're going downward forever. Let's finish these up. Look at number 19. Use this graph to f of 0. At 0, where is there a y value? There isn't, there is not one. It is undefined. It does not exist. Limit at negative 1. Oh, hold on, I'm going to trace my, let's use a different color. I'm going to trace my x and y axis so I can make this easier to spot. There's my x axis. Here's my y axis. Okay. At negative 1. At negative, I'm going to switch back to the color. Negative 1, oh, we're at 0. At 0, the limit, we're going down on both sides. We're going to negative infinity. So the function value does not exist, but we are going down forever. At negative 2, the limit from the left is up at 1. The limit from the right is going down to negative infinity. So it does not exist. It's undefined. At x approaches infinity means to the right, as we go out to the right forever, it does this level off. It has a horizontal asymptote up at 2. And at x goes to negative 3, 1, 2, 3, negative 3, we're at negative 1. And number 20 says, know the difference between removable and non-removable discontinuity. Non-removable are vertical asymptotes, and they cannot be canceled out. Removable are holes, and they are, you can factor and cancel. Factor, cancel. Non-removable was a vertical asymptote, and that was a number over a 0 in the denominator that didn't cancel out. Now when a limit doesn't exist, well, when the limit from the left doesn't equal the limit from the right, when we have one-sided limits don't exist from both sides. When else? When a function oscillates. So if the left and the right don't agree, if it oscillates, or if it increases or decreases without bounds, that goes to infinity. And those are the main two are basically when a function oscillates, or when the limit from the left does not equal the limit from the right. And that's the end of the review. Good luck.